Hello students, welcome back to Organic Chambers YouTube channel. In this video, I am going to explain conformations of cyclohexane molecule by solving the given question. By now, you might know what is conformation and what are the conformational structures for cyclohexane molecule. If you don't know, then you can refer this video to understand the conformations of cyclohexane. What is conformation? You know that in alkane molecules, due to free rotation of carbon-carbon single bond, it forms different structures and we call them as conformations. For cyclohexane molecule, it exhibits different conformational structures called chair conformation, twist chair, boat and half chain. What is this chair conformation refers to? Why the molecule should exhibit different structures? This can be explained by angle strain in the molecule. What is angle strain? When you look at cyclohexane, its structure is similar to hexagon. In a planar structure, we know that the bond angle will be 120 degree. But we know that in alkane molecule, the carbon is sp3 hybridized, hence the bond angle will be 109.5 degree. You can see here the bond angle between a hexagon and sp3 hybridized carbon, there is a difference, and due to that difference there is a strain in the molecule and we call it as angle strain. But in cyclohexane, since there are 6 carbon, there is a free carbon-carbon rotation. There will be twisting of the carbon-carbon single bond and it can avoid this angle strain. How? Just imagine here students, say let's assume the bonds are here like this and this carbon goes up somewhat like this. And what about this carbon? It goes down like this, okay? Something like this where the bond angle will be almost as that of a ideal bond angle. That means what? The ring structure undergo twisting, bending, puckering and it will try to attain the bond angle of sp3 hybridized carbon, and this conformation is called as chair conformation. This chair conformation can also be written like this. This is a proper representation of chair conformation. This undergo further twisting, bending, etc. and it forms its mirror image like this. This is also chair conformation. Both of them are chair conformation because it looks like a chair. Just imagine students, so there is a guy who is relaxing on this chair like this. So that's why it's called as chair conformation. It's quite easy to remember that way, isn't it? Now, these two are interconvertible. This changes to this changes to this. And it won't happen in one step, okay? It happen step by step. While doing so, it will form different structures. What are the different structures? As you might know, the different structures or conformations are chair, twist chair, boat and half chair. How do you convert them? Since you are preparing for competitive exams like NEET or IIT, you should know how these structures are interconvertible and what is their energy and how it is related to their stability. Only then you can answer questions like given here. Now, let's quickly write down the different conformations of cyclohexane. Students, I am going to give you a simple trick how to write the structures, okay? Please understand this. So this is a chair conformation. These are the two extreme ends, isn't it? This is where it converts from here to here, here to here. Then what are the different steps? So in between these two, there is a structure called as boat conformation, like this. Because it looks like a boat, just assume there is a guy who is rowing in the lake or a sea, right? So this is a boat conformation. So before it changes to boat, there will be two more structures. How to write it? So simply you write down this as it is. Okay, if this is chair, right? If this is chair, what I'm going to do is I'm going to move it in this direction, because look here, ultimately it's going down, right? So when it moves like this, it's somewhat like this, okay? And what do you call this? It's a half chair. You're trying to get it in the plane, so it's a half chair. And what happens to this half chair? It's not so stable as this, because the bond angle here again for this carbon I'm talking, it's 120 degree. So it wants to avoid that angle strain. So what it does is it will undergo some sort of a twisting. Okay, that's why, say these two are carbons, these two are carbons, okay? Then there is one carbon here, one carbon here, like this. And what do you call this? Because of the twist, we call this as twist boat. Before it becomes boat, it is becoming twist boat. So from here to here and here to here. What happens to this twist boat? So this twist boat will become boat, right? So for now I will write only one side, okay? Yeah. And then what happens to this? Again, it changes its angle, okay? Although it looks like it's mirror image, okay? So you can write like this. There is no carbon here, okay? You have to remember the carbons are here. 3 carbons here, 3 carbons here. Then what should happen? Same here, like half chair. But how do you write half chair? As I was telling you earlier, you have to correlate to the final structure. That would be much easier. Okay, because it's very hard to imagine for a three-dimensional structure, because we are writing three-dimensional structures in two-dimensional. That's why, right? So ultimately what happens? This carbon goes up and it will form this structure. It won't stop here. It comes back. It changes to this, this changes to this, this changes to this, and this will change to this, like this. So these conformations are causing stability to the molecule from when it changes from this state to this state to this. That's why it will undergo conformation. Okay, so this is about the different conformational structures. Now let's see their stability. You have to remember the different structure, and also you can compare what is given in the options also, right? We'll read out the question, we'll solve it later on, but just identify what are the structure, compare here. Okay, this looks like this, right? So that's why I will write it as twist boat. Okay, what about these two? Obviously they are chairs, right? A chair here and a chair here. But what about this? It looks like this, okay? You can see here the three-dimensional, it's given like the molecule is waved from here. That's why it looks like this. But they are one or the same. It's boat. Okay, so once you have identified all these structures from the conformations I have written, now we can read the question carefully. Okay, which of the following is the most stable conformation of bromocyclohexane? Well, in order to understand this, first you need to know the stability of just the cyclohexane molecule of different conformation I'm talking. Okay, so let's write down the different stability. How do you know stability? Depending on their energy. We compare their energy. Higher the energy, lesser the stability. So that you already might know. If you don't know, you can remember this, students. More the energy, lesser the stability. So stability of different structures is the chair conformation is more stable because all the bond angles will be close to the ideal bond angle. Okay, then we have twist boat. Why twist boat is less stable than chair? Because one of the bond angle will be 120, and the boat is not so stable because we call here the hydrogen present here will be usually having some repulsion or hindrance. That's why boat is less. And then we have half chair. We have half chair. Okay, so this is the stability of different conformations. Okay, now whenever we have hydrogens, how do we write these hydrogens? I can teach you that as well here. The hydrogens are written like this. First you write down these hydrogens in a straight line, like they are vertical, right? So and we call them as axial hydrogens. Okay, so 1 2 3 4 5 6, there are 6 axial hydrogen. Now what about the other 6 hydrogen? Because in cyclohexane there are 12. So how do you write that? You will write these hydrogens in such a way that it's parallel to, so if you count from here 1 2 3, so it's parallel to this bond like this. Okay, what about here? This will be parallel to this one, 1 2 3 like this. Okay, what about here? It will be, see here, 1 2 3 parallel to this one. That way it would be easier. Okay, what about here? So we have to write it parallel. See, this one is parallel to this one. That way it would be easier to remember where the hydrogens are. And what do you call this as? It's called as equatorial hydrogen. So we will have 6 axial and 6 equatorial hydrogen. When all of them are hydrogens, right, the repulsion or the steric hindrance will not be considered because hydrogen size is very small. But whenever you have a bulky group, that is methyl, bromo, tertiary butyl, so anything other than hydrogen we are talking here, they always prefer to take up the equatorial position. This is the key factor which will help you to answer this question. Okay, so equatorial position. Why equatorial position? When it occupies equatorial position, there won't be a steric hindrance with the other neighboring hydrogens. There is less steric hindrance, you can say. Suppose if it is in the axial, then you can see that this will have steric hindrance with the hydrogens given here. Okay, that's the reason. Okay, so now due to the bromine being equatorial position, we have established that that is the most stable. Let's answer the question now. Chair is the most stable, so the answer has to be either 3 or 4. Right, because we know that boat and twist boat are not stable, but we have 2 chair. Look at the position of the bromine. The bromine here is equatorial because the vertical lines are axial, I already told you. So here it is equatorial, here it is axial, and we know that when bromine is in the equatorial position, it is more stable. That means what? The third molecule is more stable. Where do we have 3? We have 3 as option C. Therefore, option C is the right answer. I hope you have understood the concept. If you have not, you can re-watch the video, you can pause, you can think, and then you can go ahead and answer the question. Thank you for watching this video. Until next time.